Okay, so we have Professor Kim from Sejong University talking about Lattice NRQCD calculation of the thermal Sommerfeld factor.
Thank you. I'm going to talk about the chemical equilibration rate computation lattice, which is related to the getting this Sommerfeld effect on the lattice. This is the work done in collaboration with Mikolaine of Bern. This is the archive numbers. It's going to be published in JPEG. Okay, so this is the outline. I'll just introduce, and the method itself is somewhat unusual. Doesn't use spectral functions, so I think I need somewhat longer introductions to how we can compute these things. Then I will talk about the method, and I will show the result and the discussions. So I'm talking about some real-time quantities like a chemical equilibration rate, and we usually talk about in terms of spectral functions, but this doesn't use spectral functions, so I do not have to worry about this post problems, which is a kind of relief. Okay, so what we mean by chemical equilibration rate in the thermal environment is summarized in these formulas. That's how you get in perturbative calculations. You compare the Boltzmann equations, and you compute how the number density rate changes. So the chemical equilibration rate means if given temperatures and how many heavy quarks you can find, and in thermal equilibrium, this is the numbers. And there is this S bar factors is called Sommerfeld enhancement factor. The idea is that compared to trill levels, if you have a slowly moving particles, they will be enhanced. And the reason is that this kind of phenomena, if I have two heavy particles, and they get annihilated, then since it is slow, these diagrams, these propagators will behave like this, coupling constant here and there, and the propagator is like 1 over v, and since v is small, since this is a non-relative thing moving slowly, then this becomes order 1, and you have to presum it, and that's what the Sommerfeld enhancement factor will tells us. So just comparison between trill-level matrix element to the presumed matrix element. And there are two. One is the color singlet combinations, and the other one is the color octet combinations. And this is the presumed result. And this problem happens in many different contexts. And the other areas of application is the dark matter core annihilations. That's the reason I showed these funny particles, which you don't see in the QCD. They have some heavy dark matter, and they interact with gauge interactions in electroweak sectors, and they annihilate to something else. And this is a typical diagrams which happens in the dark matter core annihilation scenarios, and there is also applies. So our result actually can be applied to the dark matter core annihilations, and we are working on the extending our result to that problem at the moment. All right. So how do we compute this Sommerfeld effect? Normally, one based on one's understanding on the Boltzmann equations. So n is the number density. So change of number density is the difference between the equilibrium value and the value at time t, and one can consider this as two terms. One is the loss term and gain term. So if the number disappears, that will be lost, and if number produced, then it will be gain terms. And in the equilibrium, it will be like that, because this is 0. Essentially, in equilibrium, the number doesn't change. There will be fluctuations, but the average number doesn't change. So in Boltzmann equation formulations, that's how you define the chemical equilibration rate. And microscopically, one can compute using these perturbation theories. And this denominator is the equilibrium number density, and the numerator is the incoming particles and outgoing particles. If it is bosons, you have Boltzmann factor for the Bose-Einstein distributions, and for fermions you have a Fermi-Dirac distributions, and this is the matrix element I was talking about. Wow. Right. Anyway, and as we know well, the QCD is highly non-perturbative, around 1 to 2 TC we are interested in. So this Boltzmann equation cannot be applied. So D3 and Miko developed the formalisms which can be generalized to consider chemical equilibration rate in terms of Langevin equations. And this is a short summary of what they mean, I think. So treat that the number change as a Langevin processes. So one has this Langevin equations, and the width of this random noise has information about this chemical equilibration rate. One can solve these equations, and that's what you get. So if I consider the density correlations like this, then that has this form. And as one can see, there are two parameters, so if one needs additional information, so if one consider the time derivative of these correlation functions, and then you can get the other informations. And in frequency domains, that's what it is, and then you can consider that as these two ratios, and you can define this chemical equilibration rate as the width of the noise and the normalization factors of the susceptibility. Now that's all in the real-time formulations. To compute these things, we need to go to the Euclidean time and Euclidean space time, and so one has to generalize these things to Euclidean times. And well, just you do weak rotations and consider the same thing. And then if I compute these things, and if I compute the spectral functions, the omega chem or the chemical equation rate is related to in this way. So one might need to get the spectral functions. But in the heavy co-effective theories, these things can be computed using this complicated object, which is you start from the actually the Hamiltonian here in non-relativistic theory actually count the number of heavy quarks. So actually this is related to number density. So you measure the number density at the 0 time, then you go to tau, and there is this number changing annihilation fork of operators, and in Euclidean time that becomes this has these forms because of the analytic structures are different from Minkowski space and the Euclidean time. At the end, what we want is the matrix element. So one just need to know the tau goes long tau limit, but in final temperature you have to go wrap around. So after the complicated derivations, you arrive at this form of matrix element you need to have access to. Then the omega chem, we need to define the chemical equilibration rate. It's just 2-point functions, and even that is just from 0 to plus. 0 plus means you start from tau equal to 0 in Euclidean time, then wrap around all the way. That's what 0 plus means. And this has the information about this omega chem. And on the lattice, one need to compute these three things. This one is like a heavy quark just propagating, and this one is the heavy quark propagating sandwiched with anti-heavy quarks, which is related to singlets. And this is the different color combinations. And using these three lattice quantities, one can define this Sommerfeld factor for the singlets and octets. I think I'm pretty fine. All right, so how do we, on the lattice, I know I'm a lattice guy, so I have to give these numbers. So for your informations, we are using this second generation fast sum configurations. Has 2+1 life flavors, somewhat heavy pion and kaon mass, and the temperature is changed by changing n tau time slices. So it's a fixed scale, so you just change n tau, that changes your temperatures. And the transition temperature in this setup is somewhat higher, and the spatial lattice spacing, the heavy quark mass for the bottom one is like 2.92. And this configuration has been used for different studies like electric conductivities and the bottom studies, the spectral function studies. All right, so we are doing the heavy quark NRQCD evolution, so it's initial value problems, unlike the relative steep heavy quark case. So you just evolve using the Schrödinger equations, and we are using v to the fourth NRQCD Lagrangian, so there is a higher order terms as well. And this is the result of the computations. So for different temperatures and different quark mass, and for highest temperatures, we also ran the additional masses. And this is the result of computations. So right figure is the Sommerfeld enhancement factor for the singlet and octet. So octet is a repulsive, so it stays as order 1, but surprisingly the color singlet part, which is attractive, is a huge enhancement. So it's it's like 100, even 1,000, compared to order 1, what we would expect in perturbative analysis. And the left panel is the mass dependence of that result. And there are two masses, one for the bottomonium and somewhat heavier charm. And so one can see that mass dependency is quite small. So the surprising result is that you have huge enhancement, not just factor 10, it's just 100 or so. When we get these numbers, we are, that something is wrong, because it's, you don't see, like factor 100 increase in the numerical numbers. And this is the leading order perturbative calculation Mikko did, and initially that was his expectations. The red is the color singlet, and the blue is the color octet channels. And this is repulsive is order 1, and perturbation somehow increase the singlet channels, but not like that. So he went back to his old calculations, and what he found is that if there is some complicated subthreshold structures, like bottomonium case, you have unmelted bottomonium surviving in these temperatures. So if you have such a spectral functions, then you can explain this large enhancement. So this lattice result can be understood when we have this complicated spectral behaviors in finite temperature. Okay, right.
Lots of time.
Right. Okay, so we did first chemical equation rate computations for heavy quarks. And this is the real-time quantities, but through theoretical formulations, we could compute things in the Euclidean lattice, which does not require the analytical continuation. So you don't need to worry about this spectral function reconstructions. And if we put numbers in, this is actually bad news. Not bad news. It's already known that the bottom core doesn't thermally equilibrate the number density of bottom core in current generation of heavy core experiment. Lifetime is like a few tenths of Fermi, and this comes out like 150 in terms of order of magnitude intervals. So, given lifetime of covalent collisions, you don't have the equilibrations, chemical equilibrations. Kinetic equilibration you achieved. That's one of the other results by Miko and Olaf and Francis, but not chemical equilibrium. And what we found is that there is a large enhancement because of this surface threshold boundary state effect. And the same thing can be applied to dark matter case. And in other words, people consider this dark matter core annihilation scenarios to understand the anomalous diphoton coming from center of our galaxy. And that sort of scenarios one need to worry about this enhancement. And there, if the dark matter is interacting strongly, for example, and has complicated boundary space structures, then you would be surprised that there is there will be enhanced more than what you expect. We are studying such things, and some non-abelian gauge theory interacting dark matter cases. What Miko and I doing is there's like factor 80 enhancement compared to ordinary considerations. So it's a nice discovery for that. Thank you.
Okay, lots of time for questions. Any questions? Yeah.
Thank you. Sorry, maybe a technical question. I mean, NRQCD has zero temperature. The problem of not having a continuum limit, you cannot take you have power divergences in that part of the lattice space in the energy spectrum. So how does that work here? Do you have such a problem, or it's fine?
Well, actually, you do not have to worry about it because the enhancement factor comes out as a ratio. So the divergence we are talking about is like large n behaviors, and that to the leading order cancels out in both numerator and the denominator. So this piece, m-dependent piece, and the divergence, perturbative divergence associated with actually cancels in this ratio. So for the leading order, you don't have to worry.
Yes, thank you.
Eric?
So if you would extend the calculation to higher and higher temperature, eventually the bound state would melt again, just like we expect. So for the dark matter application, there would be a range of temperatures where the enhancement is present and higher.
There is the normally, I don't know about dark matter. Can you imagine? And the temperature range they are considered is like a mass divided by 20. Mass divided by 30 ranges. So it's reasonable ranges. In that range, if we have a non-abelian gauge interactions, the boundary state spectrum will be complicated. In that case, you can have like factor 80 enhancement. So it's a complicated questions between boundary state survival, as you say.
So as far as I understand, your result is independent of the mass.
Yeah, that depends slightly, but not that much, because this two is this circle is the Potomonium case, and square is somewhat lighter, and it still says 100 enhancement. Yes.
Because one may assume that at least the charonium bound state may disappear at some temperature around there. And that may then should give an effect here.
Yeah, but this is still 2.4. It's not like
Oh, yeah, right. It's quite heavy.
yeah, it's still heavy.
Okay, any further questions? Okay, next speaker. Okay, now our final speaker of the session.